this next section, we're going to talk about coal and nuclear power. So coal is a multi-stage process to actually get to where it is. We talked a little bit about peat and the last one and how people could cut it out of the ground. It's like very deep areas of vegetation. It's not like grass. It's more like moss, kind of. It's like peat moss, and it grows down deep. Um, and they would cut it out and they would burn the bricks of it. Well, if it gets buried and compressed over time, that's actually what becomes coal. And so the chart that you see in front of you is as you put it under more heat and more pressure, you get different kinds of coal. So lignite is the youngest coal, if you will. Um, it's in limited supplies, and a lot of that's because it's the closest to the top, and so it's been mined a lot. So there's not a lot of it left in various areas. But bituminous coal is used a lot. It produces a lot of heat. There's a lot of it. Unfortunately, it has a lot of sulfur in it, and so when it's burned, it produces sulfur dioxide, which is not a good thing. Anthracite is the most sought after coal, and that's because it's the hardest and the densest, and it produces a lot of heat, but it has a lower sulfur content. So if you've ever seen the commercials where they talk about clean coal, this is the one that they're talking about. So it's still not clean. It's still producing sulfur dioxide, but it's producing less than the other kinds of coal are. So we have a lot of coal here in the United States in the Appalachian Mountain Range area. Russia and China also have a lot of coal. Because we had so much of the planet at one point in time was temperate and tropical and had a lot of vegetation, and that all got buried over time, and then the continents shifted and mountains got built, and that put areas under pressure and caused heat. That's why we have all these different coal beds around the world. So the biggest one for us is basically all along the Appalachian Mountains. So the east coast of the United States wasn't always attached to the rest of the mainland. Hundreds of millions of years ago, the east coast slammed into the rest of the country, and when it did that, it pushed together as the plates were coming together, and that formed the Appalachian Mountain Range. But all those swamps and areas were along the coasts of those two different continents at the time, and when all the shifting and moving happened and burying happened and then mountain building happened, it created these really rich coal beds all along the east coast. We do have coal in other areas of the country too. We have some in the west. There's a little bit here in Arizona. It's mostly up in northern Arizona on one of the Indian reservations. That's one reason why we don't have like coal factories or fired factories here or anything, because we would have to ship coal in from everywhere in order to be able to use it. So it's not like it's something that's a local resource for us. So obviously we've got lots of it, which is an advantage. We could be entirely dependent upon that for a long period of time. Unfortunately, not everything in our country runs off of coal, so we couldn't like just switch over tomorrow if we needed to. We would have to do something with it. But they can actually make coal into a syngas, so they can compress it and they can actually liquefy it and they can gasify it, so it can be used like natural gas. It's a costly energy-wise process, and so you lose a lot of the potential energy in that coal. A lot of it's lost to waste heat as it's making that syngas. So there's ways to mitigate the disadvantage that's of the emissions. So they have, before you get to the smokestacks, they have things that are called scrubbers that they can use to actually scrub out the contamination out of the air after the coal is burned, so like out of the smoke that comes out of the coal. The scrubbers are really big. They don't sound like they would be, but they're usually like really big, like gym size, like the gym at your high school size rooms, that they fill it with chalk, and they make kind of a slurry out of it, and that actually like scrubs out the air. They force the air to go through the slurry, and it actually cleans out the sulfur dioxide and most of the carbon dioxide out of there. It's an expensive process, but it does clean most of the emissions. They also can do what are called electrostatic precipitators in the smokestacks themselves. Basically, they run a fine wire mesh through it, and then they run electricity through that, and You have to watch a video of this sometime, but it like zaps the particles out of the air. It's kind of cool. Um, it's called an electrostatic precipitator, which helps to mitigate some of the factors. Unfortunately, they're both really expensive things to do, and so when we talk about retrofitting older factories and things like that that burn coal, it's very cost prohibitive for them. It does use a lot of land. When we talk about the ways that you get coal, especially when we look at mountaintop removal, which is exactly what it sounds like. They take the entire top off of a mountain to get to the coal, or the strip mining. There's a lot of disturbance that happens. There are some areas where they've done what's called remediation, which is where they put the area back to what it was like, or to a better state that it is now, to what it was before, and that's actually a requirement for a lot of areas that they do this. So up in Canada, up in British Columbia, there's this place called Bouchard Gardens that they actually just built ornamental gardens, like it's a big rose garden, but it's all in what was an open pit mine at one point in time. So there are things that they can do to mitigate that land use and that land damage that happened. So, whenever we talk about generating electricity, the main difference is what happens on this side over here. Because when we're talking about generating electricity, it's all about what's going to spin this turbine that spins the generator that makes the electricity. Everything else is more dependent upon the fuel source itself, but it's all about how do we make the heat to spin the generator to make their electricity. Okay, so in this case, we burn the coal heats water, the water condenses into steam, the steam rises, that movement of the steam spins the turbine, and that makes the electricity. It cools off, it comes back down as condenser, and so when you see areas that have these big stacks like this is just water vapor coming out of it. There's no contaminants whatsoever, because it's not then in touch with any of the things that we burn that would make pollution. It's all water. So they capture all the coal dust and the coal particles that come with it, and that's what you're seeing coming down here. So this is all the dust coming out and the ash, and this is where they're capturing the stuff that's in the air in that in this chamber in here after it's burned. So like the ash and stuff like that is coming in here into this filter. So this is where if they were doing a scrubber, the scrubber would be in this spot right here, and then you'd have the stack where it would be releasing either, hopefully not too much of the pollutants, but if they had like the electrostatic precipitator would be in this area. So nuclear energy, once again, remember it's all about how do we spin the turbine to make the electricity. So nuclear energy is where we use uranium. So it's usually uranium-234, the isotope. They mine it. It's a metal, and they make it into fuel rods, which are what are in this green compartment chamber in here, this containment area. So all this is about containment. This is usually concrete, this kind of bubble that's over the top of it, but you'll see that, and then it's usually lead lined as well. But you see there's multiple containments to where the fuel rods are at. So the uranium undergoes fission, and the difference between nuclear energy and a nuclear bomb is controlling the fission. It's the same process otherwise that does the both. The bomb obviously is an uncontrolled reaction, and then what we want to have in nuclear power is the controlled reaction. And the way that we control that reaction is through this water that's in here, because this acts as a cooler. So this part coming in here that's pumping in, okay, we're getting cold water is getting pumped in. This reaction happens, it heats up the water, which generates the steam, which turns the turbine, okay? And then we have that heated up water, goes out, and they usually have some area where the waste heat goes with the water into it, and then they can pull in cold water. The pumps that run this are essential to making this not be a bomb and to not have problems with containment. So when in Japan, when they had the tsunami that hit, so first of all, the earthquake shook and it knocked out the power, and so they were using at Fukushima, and they were using the backup generators to run the to run the pumps to make sure that the cooling rods stay cold or stay cool enough and didn't have an uncontrolled reaction. But when the tsunami hit, it swamped out the generators, and so they were no longer able to pump the cool water into this in order to cool it down. And so it just kept heating up and heating up and heating up. It ended up venting radiation out of the top. They had a small explosion. They did not have a giant mushroom cloud or anything like that. They had a small explosion that damaged the containment, and that's why there was radiation leakage. And then also in the ocean water as well. But they were just using, they had firefighters in there that were, for hours and hours and hours, they were just using ocean water to try to keep it cool to keep it from melting down. So after they're spent, after the fuel rods are done, they have to do something with them, and they're still warm. They still are releasing radiation, just not enough for it to actually still be doing its job in the nuclear power plant. So what you're looking at here is a pond of water where it's concrete lined and lead lined and all that, and they're cooling down the rods. So they're submerged in water to cool them down, and then they store them in containment containers. So at this point right now, we don't have enough storage facilities to actually take all of the nuclear material off-site. There is one area that was being constructed. Yucca Mountain was being constructed to house nuclear waste. If we were to take all of our nuclear waste all over the United States and put it in Yucca Mountain, it would be full. And so we need to start thinking of other options. Right now at Palo Verde Nuclear Power Plant, all of the waste that has been generated on site is still on site, which is a bit of a security concern. So it's safe where it's at, and you'll see that they have space in between it. They have monitoring things. They're going to do the same thing in Yucca Mountain. They have everything kind of spaced out and where they can see in between it, and they can make sure nothing's leaking or anything like that. It's just having all of that radioactive material in one area is a little bit concerning. So it's not as, it was seen at first, when we first figured out how to control the reaction, to not just make a bomb out of it. There was a big hype for this could be like the energy source of the future. We wouldn't have to use as much fossil fuels. It's cleaner when you're looking at just the process of making electricity from nuclear power. There's no emissions from this. As long as all the radiation stays contained, it's pretty clean. But it hasn't quite made it over that hump yet. We have a lot of nuclear power plants in the United States, but as far as like replacing other non-renewable resources, it's really expensive to build and maintain a nuclear power plant. And then it's also a little bit of a tricky system, and so we got to make sure that we get all those quirks, taken care of, because if something happens at a coal-fired plant and there's a fire or something like that, you'd have a small area around the plant that would be in danger. But if something happens at a nuclear power plant, your area that could be impacted is much greater, so they have to pay much more attention to what's going on in those areas. We've had some areas where there was some poor management, and so we had some accidents, like in the Ukraine at Chernobyl, where it was primarily poor upkeep of the system, and I shouldn't say nobody, barely anyone lives around Chernobyl, and that happened 35 years ago or so. We had another accident here in the United States, in New York at 3 Mile Island, which was not nearly as significant as the event that happened at Chernobyl, but did cause some injury and some concern in those areas. And so some of those things are really kind of holding back the public from wholeheartedly wanting to move forward with introducing more nuclear power plants into the United States. So this is Chernobyl. Once again, it was human error that caused this to happen, and because we're talking about radiation, it's not just what happens with the explosion, it's also what happens, the long-term effects, because the half-life of uranium is quite long, and so it persists and hangs out in the atmosphere. So once again, we've got the advantages and disadvantages. We have a lot of uranium. We have a lot of it available to us, and so really the primary environmental impacts are the mining part of uranium. We get a lot of heat out of it. There's a lot of waste heat just because so much energy is created that we can't possibly capture it all. But the energy that we can capture, we get a lot of it that we can use. So the risks when you look at, I love the exploding picture here, that doesn't happen very often. Like I said, we have right now 3 significant events that have happened over the course of almost 70 years of utilizing nuclear power. And one of those was not really as big as the others. And so it has been a relatively safe source of energy. Like I said, a good portion of our energy actually comes from a nuclear power plant here. So on the other hand, though, it's so expensive, and so it does require a lot of government subsidies in order to be able to continue. We could not afford to pay for Palo Verde here in the Phoenix area on our own without government subsidies. And we can never, we have to be real careful where we build nuclear power plants. Unfortunately, in Japan, Japan is very seismically active, and so the probability of having an earthquake where one occurred near Fukushima and then the resulting tsunami, while that particular event was big, it's not completely out of the realm of possibility because there's plates that are moving there. It's on a subduction zone, and there's a lot of earthquakes that happen in that area. We don't get very many earthquakes here, so it's a bit safer of an area when you're looking at catastrophic events or natural disasters causing accidents. So then we got to figure out what to do with this storage. We got to store the waste. We talked a little bit about Yucca Mountain. That's the bury it deep underground. The shooting it into space, there's actually laws and treaties that say you can't actually detonate a nuclear weapon in the atmosphere at all. So I imagine that there's probably some prohibition from shooting up nuclear waste as well, because the same kind of thing would happen if that the rocket that it was on actually exploded. So some other thoughts were to bury it in the Antarctic ice sheet. Probably not the greatest idea. Burying it in the deep ocean floor that's geologically stable. So basically drilling down. It's kind of like reverse oil drilling. You drill down, they would inject it down into the ocean floor, cap it. This last one would actually, if they could figure out how to do this, to change it into harmless or less harmful isotopes, that would be a wonderful goal right there. Because then we would mitigate really all of our problems if it wasn't something that was harmful.